Good morning, good afternoon, everyone. I'm Gurdeep Gill, Technical Leader at Cisco Systems. Thank you for joining. Today, I will share a practical way to build security into your DevOps pipeline for AI workloads so you get strong protection without giving up deployment velocity. Imagine it's a normal Tuesday. Your team ships a small update to an AI endpoint, maybe a recommendation model, LLM assistant, an image classifier. It's simple release until it becomes a feature everyone depends on. Traffic ramps, customers are happy, leadership is thrilled. And then the pattern changes. Not an outage, not a crash, just requests that feel a little too curious. That's the moment this session is for. I'm going to talk about why AI shifts security from static code to runtime behavior. What next generation firewalls add beyond IP and port rules. How to wire NGFW controls into CI/CD and runtime. And how to roll it out safely, monitor, then enforce, then optimize. So let's name the tension every modern team feels. The talent, velocity versus security. Let's meet Maya. Maya runs a DevOps team. They deploy several times a day because the business expects it, and honestly, it works. Shipping fast is a competitive advantage. Now, Rook is not trying to slow anyone down. Rook is trying to prevent the headline. Here's a conflict. Traditional security is built like a toll booth. It assumes changes are rare and traffic is low. But Maya's world is a multi lane highway. If every release must stop for a manual review, two things happen: delivery slows and trust breaks down. Teams route around the checkpoint just this once, and that becomes shadow security. You have seen the symptoms: temporary, allow rules that never get removed, one off exceptions with no owner, approvals done with no audit trail. Security controls that only exist in production because they're too painful earlier. And with AI, the tension spikes. You're not only protecting code anymore, you're protecting the model, the data pipeline, prompts, and unstructured input, where runtime attacks live, and the outputs, which can accidentally reveal more than you intended. So the requirement changes from approve occasionally to validate continuously. Security has to move at DevOps speed, or it won't be used. Okay, why does AI make this harder than a normal web app? AI systems are powerful, but they have a very different security personality than traditional apps. First, inputs and unstructured. In a typical app, inputs are forms and fields. In an AI system, the input might be a paragraph of text, an image, or audio. Ambiguity is a part of the design, which means old school validation rules don't help much. And unstructured input is exactly where attackers love to hide. Instructions inside normal looking text, payloads that look harmless to regex rules, prompts that try to trick a system into breaking its own rules. Second, outputs are non deterministic. With classic software, you can baseline behavior easily. Same input, same output. But AI can be probabilistic. That complicates testing, monitoring, and even incident response because reproduce a bug is not always straightforward. Third, the model is high value IP, intellectual property. Your model may represent months of training, time, and competitive advantage. An attacker doesn't need your training data if they can learn enough by observing your model through its API. Fourth, the pipeline matters. Poisoning does not always show up on day one. Sometimes it's subtle, a bias, a backdoor, a behavior that only appears later. Data provenance becomes a security requirement, not a paperwork exercise. Finally, new attack classes show up at runtime: prompt injection, adversarial inputs, membership inference. The theme is the attack surface is no longer just static code, it's a production behavior. Maya thought she was shipping software. Suddenly, she's operating a living system that learns, proves, and gets poked at in ways normal apps don't. So, what kind of control can understand behavior, not just sports? That's where next generation firewalls come in. Let's talk about the difference between a traditional firewall and a next generation firewall in a plain language. A legacy firewall is great at one question: is traffic allowed from this IP to that IP? But in cloud native AI environments, those details change constantly. Pods move, services scale, IPs are temporary. And the real question becomes, what service is this? What API is it calling? Who is making the request? What's inside the request? And is this behavior normal? That's what next generation firewall brings in. Layer 7 awareness, understanding APIs and application protocols, payload and content inspection, spotting malicious content and exploit patterns, TLS inspections so encryption does not become invisibility, behavioral anomaly detection because AI threats are often novel, identity context, policy based on workload service identity, not network location. A legacy firewall, you can think it as text the address on the envelope, whereas the next generation firewall can also understand what kind of delivery it is, who signed for it, and whether the contents match policy. So, this is the moment Rook stops being the checkpoint and becomes the person who gives Maya guardrails that don't break velocity. Now, you might say, we already shift left. We scan everything. True, but it's not enough. Shift left security is one of the best things DevOps brought to the industry. We scan code, dependencies, containers, ISC, and that absolutely prevents incidents. But let's go back to Maya's Tuesday. Everything in CI is green. No critical CVs. Terraform looks compliant. Helm charts validate. So they release ships. Then time passes and runtime reality shows up. An egress path is misrouted, and a service can talk to places it should not. A workload has more permissions than intent. A microservice becomes an unexpected bridge for lateral movement. API usage slowly shifts into abusive patterns. A time delayed condition triggers unexpected behavior. These are the problems that don't look like bad code. They look like perfectly valid behavior used in a bad way. And AI amplifies this. A model serving service might suddenly become a high value target. A connector to a data store might become an exfil path. A new feature flag might expose an internal endpoint. So the fix is not shift left versus runtime. It's both. Shift left plus shield right. Next generation firewall becomes a continuous control plane in production, enforcing policy while the system is actually running. So, how do we embed this without bolting it on? Here is the integration framework. Comprehensive next generation firewall integration. Think of this framework like weaving security into the fabric of delivery, not adding it at the end. There are five pieces, and they work best together. First, identity based access control, policy services and roles, not IPs. The survives, this survives Kubernetes churn, outscaling, and multi region deployments. Policy as code with CI validation. Firewall policy lives in Git. It gets reviewed, tested, and promoted like software. This is how you eliminate mystery roles and configuration drift. Next, encrypted traffic inspection strategy. We decide what to decrypt and inspect based on risk and compliance, selective targeted visibility, not decrypt everything. AI specific threat detection is the next. Rules and baselines tailored to model serving, training, pipelines, and inference APIs. extraction signals, injection patterns, and suspicious behavior, alert optimization, and aggregation. Because a noisy system gets ignored, we want high confidence signals that engineers trust and can act on quickly. Simple mental model you can think as CI/CD is where we prevent and standardize. Runtime is where we observe and enforce continuously. So Maya gets speed and repeatability, Rook gets enforcement and auditability, and both gets few late night surprises. Now, before we enforce anything, we need a safe rollout. Inline versus out. Let's talk about the safest way to introduce a control that can block traffic. Inline is powerful. The next generation firewalls sits directly in the path and can allow, block, or modify traffic in real time. That's full enforcement. Great when policies are mature. But inline also carries operational risk. Misconfigurations can create downtime, so you don't start then there blindly. Out of band is your learning mode. You mirror traffic to the next generation firewall so it can inspect, build baselines, and show you what it would have done without impacting production. This is the trust building phase. You learn what normal looks like at different times of day, what release day traffic looks like, which services are chatty for legitimate reasons, and what performance headroom you actually have. When you do move inline, say the reassuring part out loud. You design for high availability, clear failover behavior, and performance budgets. Security can't be fragile a single point of failure. So, Maya may wonders, I can't risk breaking production. And Rook may say, good, we won't. We will botch first, tune, only then enforce the critical paths. So, to make any of this stable in cloud native environments, we anchor policy on identity. Identity based access for dynamic environments. In modern environments, IP addresses are not identity, they are temporary coordinates. In Kubernetes and serverless systems, pods restart, nodes scale, services move, and IP based rules becomes the British fast, so we switch the anchor from where to who. Identity becomes the new parameter. Where does that identity come from? Service mesh identity, MTLS certificate proving a workload is who it says it is. API gateway identity, OAuth tokens, MTLS, API keys validated centrally. Cloud workload identity, IAM roles and managed identities attached to compute. What does this enable? Least privilege at the service level. This service can call that endpoint using this method for this purpose. So, Maya's inference service should talk to the model store and feature store, but it should not have open egress to the internet. With identity based policies that rule travels with the service across clusters, regions, and auto scaling events. And bonus benefit here is audit becomes easier. When an alert fires, you don't see a random IP, you see a real identity engineer can act on. So, once the identity is the foundation, policy can be treated like code. That's where CI/CD integration shines. Here's a mindset shift. Firewall policy should not be a special case. It should follow the same discipline as application code. Policy as code means policy lives in version control. Changes come through pull requests. CI runs automated checks. Deployment is synchronized with infrastructure changes. Rollback is coordinated with application rollback. What do we test in CI? Syntax validation, it should parse. Conflict detection, two rules fighting each other. Forbidden patterns like overlay, broad egress. Compliance checks like where sensitive data is allowed to go. Drift detection, but running matches Git. Now, Maya's team adds a new microservice endpoint. In the old world, they will open a ticket, wait days, push a hot change. In the new world, open a PR that includes the service change and the policy change and run tests automatically. Review once, deploy together, and roll back together if needed. This is how security becomes boring in the best way: predictable, repeatable, auditable. Now let's zoom, now let's zoom into AI specific threats, starting with the one that treats your API like a copy machine. Protecting AI APIs, model extraction attacks. Model extraction is a unique risk. The attacker does not need access to your training pipeline. They can learn a surprising amount by querying your inference API repeatedly and systematically, trying to map behavior. From the outside can look like unusually high query volume, very uniform automated request shapes, repeated probing of edge cases, lots of requests that don't match normal custom workflows, spikes from new identities that appear and disappear. Now, Maya sees the user's graph and thinks, great adoption. Rook looks at it and thinks that pattern is not human. What can NGWs do here? Anti-rate limiting and quotas, detects suspicious sequences and exploration patterns, automation and bot blocking signals, reduce accidental information leakage. And the key operation ideas is graduated enforcement. You don't want to break legitimate customers who are simply heavy users. So you start with first detect, then warn, next throttle, and then you challenge, and then you block based on our confidence and impact. So treat your model API like a premium resource because it is. Now, the extraction tries to copy the model, prompt injection tries to take control of the model. So, how do we protect LLMs from the prompt injection? LLMs have a charming flaw. They are designed to follow instructions. That's why they are useful. And it's why prompt injection exists. Prompt injection attempts often try to override system instructions, trick the model into revealing sensitive context, manipulate tool use, or steer outputs into unsafe territory. How to explain simply is it's social engineering, but aimed at the model. At the network layer, next generation firewalls can help in four practical ways: prompt sanitization, signals, pattern based detection of obvious instruction override attempts, request baselining, prompt length, structure abnormal characters, sudden format changes, output monitoring where feasible, indicators of data leakage, identities with repeated, rejected, jailbreak like patterns get throttled. Network controls are one layer. You still need application guardrails, strong system prompts, tool permissions, and safe by design workflows. So if your LLM can call internet tools like a ticketing system, a CRM, or a database, the biggest risk the biggest risk is not only what it says, it's what it can reach. Identity based network policy can ensure the model service cannot directly access secret stores, metadata, endpoints, or sensitive databases, even if a prompt tries to trick it. So now almost all of this traffic is encrypted. So we need visibility without sacrificing performance. Encryption is a win. It protects users and data in transit, but it also creates a visibility gap. Threats can hide inside encrypted sessions. The goal is not to decrypt everything. The goal is to decrypt what matters based on risk, compliance, and practicality. We want selective visibility, not blanket surveillance. So, hardware acceleration and crypto offload are the few tactics that we can use. So, inspection keeps up with throughput. Next, selective decryption. Focus on high risk paths, internet facing, sensitive APIs, session optimization. Reuse sessions and reduce handshake overload. Certificate pinning awareness. Some apps will reject inspections, those may need exemptions or out of band monitoring. Capacity planning, define performance budgets and size for peak traffic. Now, let's go back to Maya. Miami wonders, will this slow us down? Rook may support by saying only if we design it like an afterthought. We design it like production is infrastructure, with metrics, load tests, and headroom. Capacity planning is a security requirement. If the control can't keep up, people will bypass it. And while we are planning the present, we also need to plan for the crypto future. PQC readiness. Let's do a quick thought experiment. If you had sensitive data that must remain confidential for 10 or 20 years, what would you do if someone could record it today and crack it later? That's the risk we call harvest now, decrypt later. Even before large scale quantum machines exist, high value encrypted data can be collected. What does readiness look like in practical steps? Build a cryptographic inventory where RSA and ECC are used. Identify long lived sensitive data flows. Those are the highest priority. Pilot hybrid approaches where available, classical plus post quantum together during transition. Plan for performance impact. Larger keys and more computation means you measure early. Ensure your next generation firewall platform can evolve by firmware software updates to support new algorithms. This is a planning message, not a panic message. You don't migrate everything overnight. You start with pilots, measure, and prioritize systems, handling long lived sensitive data. So, Maya wants to ship this quarter. Rook wants to make sure the data is still protected years from now. So, we go in phases. Now, let's come back to day reality. Alerts, because security that cries, pulse gets secure. If your alerting system is noisy, people stop trusting it. It's like a smoke alarm that goes off every time you make toast. Eventually, someone disables it. To avoid that outcomes, baseline first. Out of band monitoring teaches you normal behavior. Use anomaly scoring. Not every deviation deserves an alert. Aggregate events into instance. Tell a story instead of dumping logs. Enrich alerts with context. Service identity, criticality, destination reputation, and recent deployment changes. Continuous tuning. Feedback loops improve precision over time. Make it tangible within some example alert narrative. For example, service interference API, identity service account, change context, deploy version 1.2.3 10 minutes ago. Observed unusual egress to new destination. Confidence high. Suggested action, confirm destination, block if unapproved, or rollback. That's an alert an engineer can act on. This matters for DevOps adoption. My team will only embrace security telemetry if it helps them decide quickly, not if it creates a second on call job. Rook's best moment is when an engineer says this alert is actually useful. So, what's the practical rollout? Here's a roadmap you can take back to your team. Let's close this story. Maya and Rook don't fix this with one giant security project. They do it in phases, and each phase earns trust. Phase 1, out of band monitoring, 4 to 8 weeks. Meter traffic, build baselines, tune detection, performance assumptions, drive false positives down. Phase 2, policy as code plus selective enforcement, approximately 6 to 12 weeks. Move policies into Git, validate in CI, begin inline enforcement on low risk paths, practice rollback like a fire drill, so it's a calm when you need it. Phase 3, AI specific detections, 8 to 16 weeks. Add protections for model extraction, prompt injection patterns, and AI API abuse. Expand coverage with graduated enforcement. Phase 4, performance optimization. Post quantum pilots, TLS inspection throughout, and acceleration if needed. Start PKC readiness testing for long-lived sensitive data. Deployment velocity unchanged or improved because policy changes are automated. False positive rate drops over time, not up. Latency stays within budget. Clear audit trail for security policy changes. Fear emergency allow all exceptions. So, main key takeaways are security can be continuous and automated without slowing deliveries. Shift left is but runtime protection is where real exploits happen. AI changes the threat model, so controls must be identity aware and behavior aware. Security works best when it moves at the speed of DevOps because it's a built into the system, not bolted on later. Thank you.